Okay, the second part of the projectile motion stuff is what we call inclined projections. So in other words, you throw it at some sort of angle. So here's our thing being thrown at that angle with speed u. So again, we still split it up into the vertical and the horizontal components. So the vertical component of the initial velocity is that, and the horizontal is that, just using a bit of trigonometry. This x down here, that's the distance that it travels in the x direction to where it lands again. And so we've got a few things. So we need to split it up into vertical and horizontal. So let's start first of all with the horizontal direction. So in the horizontal direction, that green one there, that's our velocity in the horizontal direction, u cos theta. That's what our u is. Of course, that's also what v is, because it doesn't change, because the acceleration is x. Sorry, not x. The acceleration is 0 in the horizontal direction. The distance it travels is x, whatever that is, and the time for the flight is t, whatever that is. So using the x equals ut plus a half at squared. I think in your notes it's got s here. That s and x are interchangeable, depends on which book you look at. So when we do that, x, the distance it travels, would be u, which is u cos theta, times by the time, and then a half times 0 times t squared. So we often see that as ut cos theta. So that is in the horizontal direction. Now in the vertical direction, the initial speed is u sine theta. The velocity v, that's changing, depends on where we are in the flight, so that's not useful for what we've got at the moment. The acceleration, if I'm taking up as positive, then the acceleration is down, which is negative, g. And so you look and see I've got a Cartesian plane, so in the vertical direction, up is positive, we go by that. The distance that it travels, well, it's in the y direction, so I'll call it y, and the time that it takes for the flight is t. So again, if I use the same one, x equals ut plus a half at squared, then I get that y equals ut sine theta minus a half g t squared. Alright, so if I look at that as two equations, so equation 1 and equation 2 here, so that's x equals, and if we see we've got time there, if I rearranged that one to get time, and then I insert that in there, and then I do a whole rearrange it, which is some messy algebra, but you know, not impossible. What you actually end up with is that y equals x tan theta minus, this is the messy bit, g over 2u squared cos squared theta x squared. Now, when you look at this stuff, if we ignore these things here, which are kind of just, think of them as just numbers, and what we've got then is we've got an x term and we've got an x squared term, and the significant one is this is the x squared term. So the shape of the flight then is a parabola. Alright, that's of course ignoring air resistance. Alright. So, what have we got here? We've got an example, so let's have a look at our example. Alright, in our example we're told there a 65 kilo athlete, long jumper, leaps with velocity 7.5 metres per second, an angle of 30 degrees to the horizontal. So what is the athlete's velocity at the highest point? Alright, so our athlete projects here at 7.5. So our athlete will have a horizontal and a vertical component. Now, at the top of the flight, so the top of the flight, what we mean by the top of the flight is here. What is the athlete's velocity? Well, as we know about vertical motion, at the top of the flight, the vertical component of velocity equals 0. So there's still a horizontal component, so this bit here is the bit that we're interested in. Now, the angle that the person can jump is at 30 degrees. So when we work out what this orange bit here is, just using a bit of trigonometry, that orange bit here would be 7.5 times cos 30 degrees, which when we stick that in our calculator, 7.5 times cos 30, you get 6.50, rounding it off. The third decimal place is a 5, so 6.495 becomes 6.50 metres per second for the horizontal component of the velocity at any time. And of course at the top of the flight, the highest point, there is only that component, so 6.5 metres per second. Alright, the next one, part B, asks what the maximum height. Alright, so the maximum height, so I'm going to look in the vertical direction. So our initial speed in the vertical direction is this green one. There, and so that's 7.5 sine 30. Which when we do that on our calculator, comes out to 3.75. In the vertical direction at the top, so maximum height, so we're looking at this spot here. So remember at that spot here, there, the vertical component is equal to 0. The acceleration is the acceleration due to gravity, which is negative 9.8, because that's acting down, and looking at our diagram over here, see here's our plus and our minus, so it's plus and minus is down. And what we're interested in is x. So if I look at v squared equals u squared plus 2ax, then I got that 0 squared equals 3.75 squared plus 2 times negative 9.8 times x, and then with a bit of rearranging, negative 4.9, or positive when I bring it over, it'll be plus 4.9x with 3.75 squared, 14.0625. We should save our significant figure stuff till the end. So divide that by 4.9 and you get 2.86989 and so on. So three significant figures, x equals 2.87 metres. Alright, so finally, asks for the time to the height. Now, when we're looking at the time, if we split it up into two bits here, if we go and find this time, then the time from the top back to the bottom, again, is this time, and that's the same. So what we need to do here for this is we're looking at to the top. Alright, and so we've got all those same things before from the previous u equals, let's go back, 3.75, v equals 0, acceleration is negative 9.8, and time is what we're after. So v equals u plus at, so 0 equals 3.75 minus 9.8t, 9.8t equals 3.75, so the time to the top, 3.75 divided by 9.8 is 0.3826 seconds, so the total time is 2 times that, which is 0.76530, which is three significant figures, 765 seconds for the total flight. All right. So now we have to look at some graphs. All right, so just to, again, help you try and sort of get your head around things a little bit, look at some graphs here. So split down the middle. So the ones on the left is in the x direction. So x direction, so that's horizontal. So acceleration graph shows here 0 acceleration. So 0 acceleration, what does that mean? That actually means that our velocity stays constant. So if our velocity stays constant, what does that mean about our displacement? Well, our displacement, the graph goes like that, straight line. Straight line, remember, gradient is velocity, constant gradient. So that's in the horizontal direction. In the y direction, which is in our vertical direction, we've got acceleration due to gravity, it's negative. So that's, what does that mean? Well, when you throw the thing up, we've got a positive velocity, negative acceleration, constant, so it means a negative gradient, constant, and there it goes. So here, this is the point here where it's up the top, so momentarily at rest, and then it comes back down in the negative direction. So what does that mean about displacement? Well, if the velocity is changing, then the gradient of velocity, of course, is the gradient of the displacement graph, so the gradient of the displacement graph changes, and then we have something that looks like that. All right. Also, the other thing that we look at is symmetrical flights. And that's what I've used when I've done that example for the last bit, the time on the way up and the time on the way back the same, so it's symmetrical flights. So they're symmetrical if there's no air resistance. Alright, now something that's maybe a little bit handy is that you can find the range. So by the range I mean, so if I've got this thing and I chuck it from here and I bang to there on the ground, so this distance here is our range. And so the range R you can get from this little formula here. So V squared, how far sine 2 theta, and over G. Now that may or may not be handy, so what do we mean? There's our V, and here is our theta in here. So this is something to have on your formula sheet, but be very careful about it in that it's only for symmetrical flights, so air resistance is 0. So that leads us to air resistance. What happens on air resistance? Well, on air resistance, if we've got something that's going around like this, then whatever direction it's going to be running into air particles. So if it's going that, so depending on where it is, then there's got air particles that it's bumping into, and the angle that they're bumping into it depends on the angle that it's moving. Because remember, air resistance will oppose, so it'll be opposite to direction of movement. All right. Air resistance is a bit complicated because air resistance depends on a few things, and these are in your notes there under the air resistance thing. So the factors. So the first dot point is it depends on the speed that the thing's travelling, and if the speed goes up, then the air resistance goes up as well. And so the faster the object moves, the greater the drag force. And it's a bit more complicated than just that as well. It's V squared. So the area, so the front area, so making things streamlined. So the greater area, surface area up, then greater drag. The shape, is it aerodynamic or is it a brick? So, more streamlined. Less drag. And also, it depends on the density of the air. So on cold days, cold damp days, where you have a density which is up, what that means is greater drag. So the upshot, so it's quite complicated. So the upshot of all of this, what is it? Alright, so this diagram kind of indicates that. So here we've got a plane up the top here, an aeroplane up the top here, there it is, and it flies horizontally and it drops a parcel or something. So a food drop or something like that could be. So in reality we have air resistance. So on our parcel we've got a couple of forces acting. We've got this force here, which is our weight force, but then we've got our air resistance. So when we add those together, we actually get the force that acts in this direction. So it's going to make it go in this direction. So what does that actually mean? Well, as the diagram shows you here, with the air resistance, instead of our object landing here as we would expect, this force that's pushing it backwards means that it lands there. Alright, so it ends up being not quite a parabola. Now, what do you have to worry about? You don't have to worry about doing calculations and about that. You just need to worry about the concept, and it's always a qualitative question, not a quantitative in the exam. So by that I mean, what is the effect of air resistance? All right, so you've got some text questions there, and then there's again a whole bunch of past exam questions. Again, you need to be selective and with those, and don't forget with those exam questions, at the end of the year for a revision, you can come back and do ones that you haven't done.